Hello and welcome to Unit 1, Lecture A. Today we are going to be talking about properties of matter and energy. In science, one of the first things that we have to talk about is what units we're going to use, and we're not going to use the English measuring system. We're going to use the metric measuring system. It's also called the international system. They usually call it the SI system because it's System International. When they decided which units were going to be the standard units for science, the convention was in France, and the cube that's exactly 1 kilogram and the bar that's exactly 1 meter are in a museum in France. So, System International. If you want to know what those units are, reference table D has them listed for you. So here are some of the SI units, and I'm going to mark the ones that we use a lot. Meter, of course, and meter is a lowercase m. It's kind of long for chemistry. We tend to use centimeters for chemistry instead, but remember these units are supposed to work for all science. So you have earth science and physics using kilometers and light years and things. And then, of course, you have physics and biology using micrometers and picometers. And then you have chemistry that uses a range in the middle. The SI unit for mass is technically the kilogram, but that's way too large for chemistry. Nobody wants to use kilograms of compounds safely in labs, so grams are what we're going to use. You'll see kilopascals for pressure as standard pressure. We don't do a whole lot with pressure. Kelvins are the standard unit for temperature, and we're going to talk about the Kelvin scale versus the Celsius scale in a little bit. Moles you're going to see quite often. It's very specific for chemistry. Notice the abbreviation. The whole name MOLE, the abbreviation MOL. All lowercase, that's the abbreviation for mole. You can just leave the E on. It's really not that big of a difference. Heat, we use joules. You're kind of used to using calories for heat. Calories with a lowercase c is for heat and energy. Calories with an uppercase c is for the heat and food. We're going to use joules. It's also the unit you'll use for heat and energy when you take physics next year. Time, seconds, minutes, hours, days, years, you're pretty used to those. Volume, liter. The big conversion here, and we already put it on our reference table, is that there are 1,000 milliliters per every 1 liter. That's the one that you're going to have to convert back and forth to the most from liters to milliliters, so make sure you can do that conversion. Liters to milliliters, 3 decimal places, back and forth. Concentration is going to be either in ppms, which is parts per million, and that's for very low-level concentrations, things that barely dissolve at all. Environmental chemistry works with parts per million a lot. And then molarity. We're going to use molarity a lot this year. And notice that its symbol is a capital M. I also want you to notice that a mole, which is an amount of substance, and molarity, which is a concentration, are two different units. Two different things, two different symbols, two different abbreviations, two different equations when you look on reference table T. So try not to get the two of those confused. That's the most common mistake. Okay, so make sure you get those guys straight. Okay, so measurements, table D, mass is an amount of matter in a sample. It is different than weight. Weight is a measure of force pulling on that amount of matter. Mass is how much stuff is really there. So mass is something that will be the same regardless of location, and we use a balance to find that. Weight depends on your location, and we typically use a scale to find that, some kind of spring scale. The biggest difference, if you went to the moon and you took your mass, you should have the same amount of matter in you as you did here on Earth, so your mass will be the same, but gravity pulls on you less on the moon, so your weight will be much lower. You will see mass and weight kind of used interchangeably in chemistry, but next year when you take physics, you're going to have to make sure you get it right. So I will try to always say, mass the object, find the mass of it. I try not to use the term weight so that I'm using the term properly here in chemistry. But if you see something written as weight, mass and weight for our purposes are going to be essentially the same thing. Length, the difference between 2 points. Time, what happens between two events. Time's kind of hard to define, but that's typically how they try to define it. Volume is how much space an object takes up. When we're finding volume of a liquid, we use a graduated cylinder. When we're finding volume of a solid, we tend to use cubic centimeters. And remember that with water displacement, 1 cubic centimeter has the same volume as 1 milliliter. That lets us do the water displacement thing. You learned about that in earth science. Archimedes with the gold crown sat in the bathtub, the water splashed over. He realized the water displaced was his volume, and so he could find the volume of the crown then and find its density. Density is a derived unit. Whenever we say something is a derived unit, that means it's calculated. We don't have a piece of equipment that measures density directly. We have to find something's mass and something's volume and then calculate its density from that. So density is a derived unit, and the equation for that is on reference table T. One of the really important measurements that we're going to use a lot is something's temperature. Temperature and heat are related, but they're not the same thing. Temperature is an arbitrary scale. You can make up any temperature scale you want, but the temperature itself is a made-up value. It doesn't actually exist. You can't actually hold a Celsius in your hand. You can't feel a Celsius. The energy itself is measured in joules. Okay, so we saw that on table D, energies in joules. Temperature is the average kinetic energy in a sample. This definition becomes really important because if a test question says you have these two samples, which has the highest average kinetic energy, you're basically looking for the highest temperature. So whenever you see average kinetic energy in a test question, I want you to write above it temperature because they are the same thing. Average kinetic energy, temperature. So kinetic energy is the energy of motion. It's how much the particles are moving. Everything is moving all of the time. So all around you, everything is moving and shaking. Your desk is moving right now. The particles in your pen are moving. All of the molecules are shaking and vibrating back and forth. We don't feel it because it's a matter of scale. We're very large compared to the tiny size of these atoms and molecules, so we can't feel them moving and shaking, but they are. The average amount that they're shaking is something's temperature. So we have the Celsius scale, which is based on water. The Celsius scale was based on the temperatures that water boil and freeze at. So they took the boiling point, and on their little thermometer, they marked it. They waited and put the thermometer into their water sample. When it froze, they marked that. And then they divided this up into 100 equal degrees. So our freezing point for water in degrees Celsius is 0, and the boiling point is 100. Okay, so there's a change from that point to that point of 100 degrees. The Fahrenheit scale that you're used to for our weather was based on really odd solutions. So the coldest solution that he could make in his lab, which was an ethanol saltwater solution, and then the boiling point of the saltiest solution he could use. And so water ends up with weird numbers like 32 and 212. Not very helpful, useful numbers. Water is the most important compound. It's essential for life. If we didn't have water here and all of the cool, weird things that we'll talk about water doing throughout the year, life on Earth wouldn't exist as we know it. So having a temperature scale based on water becomes really, really helpful for chemistry because most of our chemistry is going to be done in aqueous solutions. Aqueous water, and they'll abbreviate that AQ. So most chemical reactions happen in aqueous solutions. All the chemical reactions happening in your body right now are happening in aqueous solutions. So knowing about water is really important. The Kelvin scale, on the other hand, is based on this concept called absolute zero. So Lord Kelvin decided, he was a physicist and a very brilliant mathematician, and he said, well, if temperature is this average kinetic energy, then when the particles stop moving, that would be the coldest you could really get, so that should be your zero mark. So even when something's cold, if something's negative 10 degrees Celsius, the particles are still moving, they're still shaking, and so you have all these negative numbers to your temperature scale. But with absolute zero, Lord Kelvin said when the particles aren't moving at all, that's the coldest you could get, that should be your zero. So he made that his zero. He made a Kelvin, and notice there's no degree there. He named them after himself, and he didn't make them degrees, he just called them kelvins. So a Kelvin is equal to 1 degree Celsius. This way our scales match up. So the freezing point in Kelvin is going to be 273, and the boiling point of water in Kelvin 373, and that's still a change of 100 kelvins. This makes our conversions easy. All you have to do is add or subtract 273. So there's the equation here. And if we look at reference table T, we have our density equation. Remember I said that was on table T right there. Density equals mass over volume. And right down here at the bottom, here's your temperature change. Kelvins equals degrees Celsius plus 273. Notice there's no Fahrenheit on here at all. You don't have to worry about Fahrenheit. You don't have to do the Fahrenheit conversion. You're not going to see any chemistry question that includes a Fahrenheit degrees. It's kelvins or degrees Celsius. Those are your only two choices. Beauty of the Kelvin scale is that there's no negative numbers on the Kelvin scale. They're very, very close to getting hydrogen down to absolute zero. They're in like hundreds of thousands of degrees of absolute zero, and Lord Kelvin's calculations look like they're pretty correct. So we're going to use the Kelvin scale for a lot of our math work, because with no negative numbers, you don't have to worry about temperature being in the denominator of any of your equations. All right, so if we're doing a conversion, the example here, the temperature outside is 28 degrees Celsius. What's the temperature in kelvins? You just plug 28 in. So kelvins is 28 plus 273, and then you have 11, carry the 1, 9, 10, 301 kelvins. Easy enough. Fixed points on a thermometer, you should know those in degrees Celsius and Kelvin. Absolute zero, lowest possible temperature where the motion stops. We're close to it. Mathematically calculated by Lord Kelvin, almost there in a lab. And then here, of course, is a scale showing you that from one point to the other, a Kelvin is the same size as a degree Celsius. Now I have the Fahrenheit scale on here just so you can compare 32 to 212. That's a change of 180 degrees Fahrenheit. So Fahrenheits are smaller than either a Celsius or a Kelvin, but a Kelvin is equal to a degree Celsius. A Celsius is greater than a Fahrenheit. Here's a look at the temperature scales that include body temperature, because that's probably something that hopefully one day will switch over to the metric system, and you might want to know that in degrees Celsius, body temperature is about 37 degrees Celsius. That'll be good to know if you have a fever or not. Room temperature, about 25 degrees Celsius. That correlates with 77. Obviously, our classroom is only 77 in like August, so our room temperature ends up being more like 22. That's about average in my classroom, somewhere between 20 and 22. And then absolute zero down here, negative 273 or negative 459 degrees Fahrenheit. So pretty cold. Moving on from temperature then, we're going to talk about energy. So temperature was that arbitrary scale, and energy is going to be the actual thing itself. One of the first things that I want to say, and you're not going to believe me, and it's going to be one of the things you have to be careful of, there is no such thing as cold energy. No cold energy. No negative energy. Everything exists. This is why we have the Kelvin scale. When you put something in your refrigerator doesn't make it cold. It takes the heat out of your food. So it doesn't give cold to your food. It takes heat away from your food. Heat is like cookies. There are no negative cookies. You can owe somebody a cookie. It can be a cookie you don't like the taste of, but you can't hold a negative cookie or a negative gummy bear or a negative apple in your hand. So the negative number scale for math is arbitrary. It's made up. It's imaginary. You can't actually count out negative pieces of something. You either have something or you don't. And that's the same way energy works. So the energy unit we're going to use is the joule. Look at how it's spelled. It's not spelled like a piece of jewelry. Joules, capital J for your abbreviation. It's a derived unit, so it's calculated. To find out how it's calculated, take physics, because you'll be doing a lot of force and energy there. Heat is what we typically call the kind of energy that we find from the motion of particles. So heat is the type of energy that we measure when we are using our arbitrary temperature scales. So your temperature scale is a way for you to compare how much heat two things have. Something that has a higher temperature contains more heat than something with a lower temperature. So if you take a second and you touch your desk right now, if your desk feels cold, your desk has less heat than you do. It still has heat, but it has less than you do. So heat moves from your hand into the desk, and therefore it feels cold to you because it is colder than your hand, but it still has heat. It still has a temperature. If you touch your desk and your desk happens to be warm, so maybe your laptop was just sitting there, or you had your arm on your desk, and you put your hand there and it feels warm, your desk has more heat than your hand, and heat will go from your desk into your hand. And that's going to continue until both your hand and your desk are at the same temperature. So energy gets transferred from the object that's hotter energy goes from high to low. From the object that's higher to the object that's lower. From the object that feels warmer to the object that feels colder. So if you put warm food into your refrigerator, the heat from your food goes into the air of your refrigerator. The heat from the air in your refrigerator goes into the Freon that's running through all of those tubes on the back of your refrigerator, if you've ever pulled one out to dust it off. And then the heat goes from all of those tubes into your room. So we move heat around. It doesn't disappear. When your ice freezes, the heat didn't disappear. Your freezer helps to pull it out of the water, into the air of the freezer, from the air of the freezer, out the back of your freezer, into the air of your room. We're just constantly moving it around. Okay, the equations on table T, let's take a look at those. So find your reference table. And right down here, there's a box for heat. And I'm going to zoom in on that a little bit so you can see what I'm talking about, because this one becomes important. There are 3 different equations here for heat. And I want you to take a minute and label them. This first equation, Q equals MC delta T, or Q equals MCAT. This is the one we're going to use when we change the temperature of something. Okay, how much heat does it take to boil water? How much heat does water have to release to freeze? Anytime the temperature is changing, remember a delta means change, so delta T, change in temperature. You're going to use Q equals MC delta T. Now C is specific heat capacity. How much energy does it take to raise the temperature of 1 gram of your substance 1 degree Celsius? Measured in joules per gram degree Celsius. Joules per gram degree Celsius. Okay? The next equation on that list is Q equals mH sub F. This one we are going to use when something either melts or freezes. For melting or freezing. Law of conservation says if I absorb 1,000 joules to melt a solid, that solid is going to have to release 1,000 joules of heat in order to refreeze. So this equation is used for both melting and freezing because however much heat is absorbed has to be released to do the opposite phase change. Okay, H sub F, heat of fusion. This is also a constant. Specific heat's a constant, heat of fusion is a constant, heat of vaporization is a constant. And heat of vaporization is used for exactly what it sounds like. For when we boil the substance or when we let that substance condense back down. Every substance is going to have its own unique specific heat, heat of fusion, heat of vaporization. If the state is going to give you a question with a substance, they're going to either have to give you the specific heat, the heat of fusion, or the heat of vaporization, or they're going to have to use water. So all three of these things, specific heat, heat of fusion, and heat of vaporization for water are going to be found on reference table B. So if you're using water, see table B. You might want to make a note to remind yourself that those constants are on reference table B. So let's take a look at that now. Heat of fusion, 334 joules per gram. Heat of vaporization, 2,260 joules per gram. Specific heat capacity, 4.18 joules per gram degree Kelvin. You can also use degree Celsius here because a Kelvin and a degree Celsius are the same size, so it will work. You may have learned this one in earth science as 1 calorie. At some point, they're probably going to switch earth science over to joules as well. They're trying to get all of the sciences using the same units. Water has a very high specific heat. That's a very large number. Metals tend to have specific heats in joules that are actually less than 1. That's why a metal will heat up really quickly when you put it on a flame, but it takes a long time for the water in the pot to boil. It's because water has a very high specific heat. Okay, we talked about the metric system in the intro unit, and we talked about the base units being meter, liter, and gram. Joules are also a base unit for the metric system, so we can talk about joules and kilojoules, and we can convert back and forth. So kilo being the prefix for 1,000, there are 1,000 joules in every 1 kilojoule. So if you want to know how many joules are equivalent to 23 kilojoules, remember king, hectares, duck, bits. If joule is one of your base units over here, from kilojoules to joules, that's going to be 1, 2, 3 places to the right. So 1, 2, 3 places to the right, it's 23,000 joules. If you want to go from joules to kilojoules, how many kilojoules are equivalent to 57 joules? We're going 1, 2, 3 places to the left. So this time you're going to have 1, 2, 3 places, 0.057 kilojoules. Now a lot of times I'll put that extra 0 in the front so you can see where the decimal place is. That's just a simple metric conversion. Hopefully that is pretty second nature to you now to go from kilojoules to joules, joules to kilojoules, meters to kilometers, kilometers back to meters, those types of metric conversions. Okay, 2 kinds of energy changes, exothermic and endothermic. In biology, you may have remember talking about an exoskeleton and an endoskeleton. Insects have an exoskeleton. Their skeleton is on the outside. We have an endoskeleton. Our skeleton is on the inside. Exo means released. Exo means outside. So an exothermic reaction is releasing heat. So therm means heat. Exothermic, outside heat. So it's something that's going to release heat. So it's going to feel warmer. So if you put two chemicals together and it feels warmer, it's exothermic. Fire, a really good example of something that's exothermic. Reactions that give off light also are exothermic. Endo means inside or within. So endothermic are going to be heat within. Okay, so these are going to absorb heat. In exothermic, the chemical potential energy is turned into heat. In endothermic reactions, the heat is often turned into chemical bonds. These are a little bit harder to identify just in kind of common everyday things, but if you ever get one of those cold packs where you snap it and it gets cold, that's going to be an endothermic reaction. We will look at different reactions and check to see if they're endo or exothermic. But things where you're burning. So here is a piece of potassium that's just burning in the air and giving off these lovely purple flames. Exothermic, heat and light. When you burn a match or a fire, exothermic, heat and light being given off. Glow sticks, exothermic, not giving off heat, just basically light. They typically don't get warm, but light, remember, is still a form of energy, so it's releasing energy. If you put a sensor in and during a chemical reaction the temperature goes down, so here's going from 43 and let's say it goes down to this one down here, which is telling me 5, then that would be endothermic. So if you put a thermometer in and the temperature goes down, endothermic. There's the ice packs. Okay, snap it, it gets cold, endothermic. This is a cool demo where there's an endothermic reaction in this Erlenmeyer flask. So they put a little puddle of water onto the wood block and put the beaker, the Erlenmeyer, on there. When the reaction happens, it's so endothermic, it absorbs so much energy from its surroundings that it freezes the water under the Erlenmeyer and it sticks right to the board. So it's kind of like magic. Exothermic, releases energy. Endothermic, absorbs energy. Okay, we will talk about exo and endothermic reactions quite often. Make sure you get the definition straight. That equation, that MCAT, Q equals MC delta T. Here it is in your notes. I already showed it to you on table T. You're going to use this one when the temperature changes. Specific heat, remember, for water is on table B. Okay, you're just going to have to get used to mostly what the symbols are for the equation, so that when you read a word problem, you can pick out which letter each thing in the word problem represents. So this is something that we'll practice in class a little bit, and I'm just going to do one practice problem for you here, and then we'll wrap up for today. The question says, how many joules of heat, according to table T, is Q, and so they want to know how many joules of those, so that's what we're going to be looking for, are absorbed when 30 grams of water, so grams are the unit that we use for mass, are heated from 30 to 35. So 30 to 35 is going to be a change in temperature of 5 degrees. And when I look at my equation, I have Q equals MC delta T. They want to know the Q, that's going to be my X. I have the mass, that's 30. C. C is specific heat. Specific heat is a constant, and what we need to know for C here is that it's water. So where do we go to find it? Oh, I remember. Specific heat is on reference table B. So here it is, 4.18. I can go back and fill that in. 4.18. and my change in temperature is 5. And now all you have to do is plug in the numbers and solve. So we get our trusty calculator. 30 times 4.18 times 5 equals, and we have a heat of 627 joules. Heat is in joules, mass in grams, change in temperature is going to be either kelvins or degrees Celsius, specific heat is joules per gram degrees Celsius. A lot of times we don't bother to write in all of the units because sometimes it can be a little awkward to have all of the units written in here with specific heat. So if you don't want to write them all in, that's fine, but know what the unit is supposed to be on your final answer. The questions get a little tricky when they're looking for the change in temperature. The way it's worded is a little different. When they give you the Q and they want to know the mass, sometimes that throws people off. So we're going to practice these in class and you'll get used to them. They're not scary, they're just word problems. Just know anytime that they're talking about a change in temperature, you're going to use this Q equals MC delta T equation. Okay, that wraps up today's lecture. And next class, we will talk about what matter is.